Good old L'Hopital's rule. Now, L'Hopital's rule is going to help us when we try to plug in our number. And if we get 0 over 0 or infinity over infinity, we have problems. Now, most of us would look at this and think of unit 1 and be like, well, let's just factor this out. Well, L'Hopital's rule gives us a different option. L'Hopital's rule says that if I were to plug in 2, I would get 2 squared minus 2 squared, which is 4. That would be 0. I would get 2, that would be 0. That is an indeterminate function. Okay, that's bad. All right, so I can't plug in 2. Now, I'm not going to factor because L'Hopital's rule says that I can just take the derivative of the top. So the limit as x approaches 2, let's take the derivative of the top, d dx, the top, so x squared minus 4, and the derivative of the bottom, so d dx, x minus 2, and then repeat the process. Okay, so the limit as x approaches 2, the derivative of x squared minus 4 is 2x, and the derivative of x minus 2 is just 1. So now I can plug in 2, and I can get 2 times 2 over 1, which is 4 over 1, which is 4. So L'Hopital's rule says we don't need to factor anymore. We'll just take the derivative of the top, the derivative of the bottom, try it again, see what happens, and if it works, it works, and it did. If it doesn't work, repeat. But in this case, it worked. Everyone wins. Compute the following limit. The limit as x approaches 1 of x squared minus 1 over ln of x. Well, if I were to plug in 1, I'd get 0 up here, and if I were to plug in 1, I'd get 0 down here. That's indeterminate. That's against the rules. So we have a little guy called L'Hopital's rule that we can use if we can't factor anything out and make anything disappear. L'Hopital's rule says that I can take the derivative of the top, so the d dx of x squared minus 1, I could take the derivative of the bottom, so d dx of ln of x, and try it again. So the derivative of x squared minus 1 is 2x. So I'm taking the limit as x approaches 1 of 2x, and the derivative of ln of x is 1 over x. I can plug in 1 now. So when I do, I get 2 times 1 over 1 over 1, which is 2 over 1, which is 2. So L'Hopital's rule helps me out if I get 0 over 0 or infinity over infinity, but 0 over 0 is what I got. Since I can't factor, L'Hopital's rule is the only option I can take. Calculate the limit as x approaches 0 of sine 3x over x. Now, if I were to plug in 0, I would get sine of 3 times 0, which is the sine of 0, which is 0. 0 on the bottom means that this is indeterminate. Okay, so I can't do this. Now, I can't factor anything else either, which means I have to use L'Hopital's rule. So L'Hopital's rule says this. If I take the derivative of the top, so if I d dx sine 3x, and if I d dx x, I should be able to do that, plug it in again, and see if it works. So the derivative of sine 3x requires the chain rule. All right, so I'm going to take the derivative using the chain rule. So let me just write out my limit again. Take the derivative of the outside, which is cosine. Keep the inside, which is 3x, but then multiply everything by the derivative of the inside, which is 3. So I have 3 cos 3x. And now we take the derivative of over x, which is 1. That's nice. So I can plug in 0 now. If I take the derivative, if I plug in 0, I get 3 cos 3 times 0 over 1. Over 1, useless. 3 cos 0 is the same as 3 cos 1 because the cosine of 0 is 1. And last time I checked, 3 times 1 is a big fat 3, which means B is going to be my answer, baby. So L'Hopital's rule is used if you take your limit, get 0 over 0, or infinity over infinity. You take the derivative of the top, take the derivative of the bottom, try again, repeat if necessary. No need. I got my 3. I'm done. Evaluate the limit as x approaches 0 of 2x over sine 6x. Well, if I plug in 0 in the top, I get 2 times 0, which is 0, no good. If I plug it in on the bottom, I get sine of 6 times 0, which is sine of 0, which is 0. That's indeterminate. That's also no good. So I'm going to use L'Hopital's rule. And L'Hopital's rule says that I can take the derivative of the top, so the d dx of 2x, the derivative of the numerator, and take the derivative of the denominator and try it again. Okay, so let's do just that. All right, the derivative of 2x is just 2. So I'm going to find the limit as x approaches 0 of 2. If I take the derivative of the denominator, okay, that's going to be taking the, now this is chain rule, so take the derivative of the outside, which is cosine, keep the inside, which is 6x, but multiply everything by the derivative of the inside. The derivative of 6x is just 6. Okay. Now I should be able to plug in 0. So 2 over 6 cosine 6 times 0 is going to be 2 over 6 times cosine 0. Cosine of 0 is 1, so we're in good shape. 6 times 1 is going to be 2 over 6, which is going to be 1/3. Okay, so L'Hopital's rule is used if you get an indeterminate function, which is 0 over 0 or infinity over infinity. Take the derivative of the numerator, take the derivative of the denominator, try it again, see if you get a number. We did. Everybody's happy. Calculate the limit as x approaches infinity of e to the x over x squared. Now, if you remember a lot of your pre-calculus rules or maybe even your early calculus rules, you know that this is going to go towards infinity because you grow at an exponential rate higher than that. But this is the L'Hopital section, so we're going to use L'Hopital's rule. L'Hopital's rule says that if I were to take the derivative of the numerator and the derivative of the denominator, I can try it again. Now, originally we get infinity over infinity. That's bad news. If I plug in infinity in air quotes, I get infinity over infinity. So let's take the derivative of the numerator. The derivative of e to the x, last time I checked, is e to the x. The derivative of x squared is 2x. If we plug infinity in, we get infinity over infinity again. No big deal. You can use L'Hopital's rule as many times until you get a number or what it is that you're looking for. So if I take the derivative of the numerator and the denominator again, I get e squared over 2. Now, if I plug in infinity, I get e to the infinity over 2, which is a huge number, over 2, which is just infinity. Again, we know this because we know that you are going to grow so much faster than you. The magnitude at which e to the x grows is going to be so much more than x squared because it's an exponential function versus a quadratic function. But we did L'Hopital's rule anyway, and boy did we have fun. Evaluate the limit as x approaches 0 of x squared over cotangent x. Now this is L'Hopital's rules section, so we're going to use L'Hopital's rule. And the reason why is if you were to plug in 0 into cotangent of x, you get something that's undefined. Why is that? Well, let's rewrite this out in 3 separate parts, because I'm allowed to do this. Okay, I'm going to write this out as x squared times whatever cotangent is, which is going to be cosine x over sine x. Now my issue right now is if I were to plug in 0 in for sine x, I would get 0. That's no good. So since this is a limit, I'm allowed to rip this apart any way I want. And so the way I'm going to rip this apart is I'm going to say the limit as x approaches 0, I'm going to rip apart sine and cosine and make it its own guy. I'm allowed to do that. I'm going to keep an x there and an x up here. I'm allowed to do that too. And now we take each limit separately. Okay, so I'm allowed to plug in 0. That's all good. Now, I can't plug in 0 yet, but if I take L'Hopital's rule, I'm going to take the limit as x approaches 0 of me taking the derivative of the numerator and me taking the derivative of the denominator. Now we're in good shape because I can plug in 0 into cosine and I'm in good shape. Okay, the derivative of me plugging in 0 to cosine 0 is going to be cosine 0, which I'll fix that in a minute. Okay. Now you're still 0, which means everything is just basically going to be destroyed anyway. But if I were to plug in 0, I would get 1 over cos 0, and cos 0 happens to be 1. So you become 1 over 1, which is 1, times 1, and 0 times 1 times 1 is 0. So after all of that, we get 0. But we used L'Hopital's rule and a little bit of fun math to rip everything apart, and we ended up with a nice answer anyway, and that nice answer is 0 en español. End Unit 4.